divide? Wow, and she's even using like the full term. So the goal of dividing is to take the imaginary number out of the denominator. So we don't want the I in the denominator. And she said we're going to multiply that by the complex conjugate. So if I have a 1 minus I, the conjugate is 1 plus I. If we multiply by conjugates, the hope would be then to eliminate the I from the denominator. And that's what complex conjugates do. They actually combine together when multiplying to be a real number. So we have to multiply the top and the bottom. You're going to have to do some foiling here. So if we look at the numerator, there we go. Jenny, when you FOIL the numerator, what do you get?
2 plus 5i, and then plus 3i.
Yeah. So here's our 2i, there's another 3i to give us the 5. And then the 3i and the I make 3i squared. And then in the denominator, what do you get? Yeah, eventually you get 2. So just reminding you how that works, we have the 1. Multiplying by conjugates, the middle terms always cancel when you multiply by conjugates because I have a plus I and a minus I. And then we end up with a minus I squared. So one of the properties of I, if you have an I squared, that can simplify. I squared is equal to -1. So that means the I squared in the denominator is a -1. I'm subtracting 1 minus a -1, and that's how you end up with 2, as Jenny said. In the numerator, we have a 2, and then we have the 3i squared. Well, again, that I squared is really a -1. So we're taking 2 minus 3. Well, 2 minus 3 is -1, and then we have 5i. So we multiplied by conjugates so that we have a real number in the denominator. So multiplication and division are inverse operations. So in order to divide, we're actually multiplying by the conjugate. And then it says to write it in standard form. Standard form means the real number is separate from the imaginary number. So our real number is the -1/2. The imaginary is the 5/2 I. So just taking that denominator of 2 and splitting the numerator up, kind of separating it. Everything was divided by 2, so individually they could be divided by 2. Questions? So let's go up to number 58. Number 58 doesn't have 1 minus I or 1 plus I. It just has 2i. You still have to multiply it by its conjugate. So if I'm multiplying 2i by its conjugate, Kaden, what would the conjugate of 2i be? -2i. So I can't just multiply it by 2i. It must be multiplied by the conjugate of that. So that would be multiplying it by -2i. So again, if we multiply here, taking the 6 times the -2i, and then the 10i and the -2i is -20i squared. On the bottom, 2i and -2i make -4i squared. So Kaden, what's your numerator become? Yes, I'm just going to pull that 20 first, and then -12i, and then the denominator is just 4. Yeah. And then simplify that because it should be in standard form. So we want to divide each by 4, and Kaden, that makes 5 minus 3i. So conjugates would be the way that you're actually dividing with imaginary numbers. You want to get the I out of the denominator, just like radicals. We can't have a radical in the denominator. You cannot have an imaginary number. We also can't just have a negative in the denominator as well. So fractions, when you're talking about numbers, the only thing that can be in the denominator of a fraction is a whole number, which means positive. Questions? Anyone at home have questions on the imaginary numbers? So the second group of problems that students had questions on were 64 through 67, I believe. Let me look, I tried to circle them. Oh, no, let's look at 62 first. And then we'll look at that group of problems from 64 to 67. So number 62 is similar to 63. It looks like this group of problems are very similar as well. It says write as a product of linear factors. So that means essentially we want to factor it completely. We want to break down the problem as far as we can. In 62, we have x to the fourth minus 16. So Hannah, how would you start factoring x to the fourth minus 16?
You would find out the rational zeros.
Yeah, so we want to find out all those zeros. Is there a way that you could try and factor it?
Well,
Yeah, difference of two squares. What would that be?
x squared plus 4.
Excellent. And she said, we want to find all the zeros. So I could set that equal to 0. So this second factor, she said x squared plus 4, x squared minus 4, because it's a difference of two squares. When you have x to the fourth, it breaks down as x squared and x squared. That second factor, Hannah, of x squared minus 4, that can continue to break down to become?
X plus 2.
There you go. So that's still a difference of two squares. And then the other part, that x squared plus 4, well, if we set that equal to 0 and find the zeros, we can then take those zeros and make them into factors. And that should be a negative. I'll make it like that. And then Hannah, the other two factors, when you take the square root of negative 4? Right. So those would become then our other two factors. The square root of a negative is an imaginary number. So we would end up with x plus 2i and x minus 2i. So as a product of linear factors, I have 4 factors because the power is 4. So I would just want to make sure that we're writing all 4 factors. Whatever the power is should correspond with the number of factors. Linear just means that each one of those parentheses, each factor should just have a power of x to the first. So you shouldn't have x squared remaining because that's not linear. So if the power is 4, I have 4 factors to multiply together. Questions on 62? So the next group of problems were 64 through 67. It looks like they're all very similar. The directions for these group of problems want you to find a polynomial, and they do give you the power. So 64 says find a third degree polynomial. So that means my end polynomial should be x cubed. It gives you zeros of 0, 2 minus I, and 2 plus I. So if these are zeros, that means x is equal to that value. So a 0, x is equal to 0. X is equal to 2 minus I. And x is equal to 2 plus I. That's what a 0 means. Grant, what could you do with a 0 to try and find a polynomial?
Could you plug it into x parentheses and minus 2 minus I?
Yeah. Excellent. So we could take a 0 and make it into a factor. So a 0 becomes a factor, and once we have a factor, we can FOIL it or multiply it together. The last 0 is just an x in front. because it's just x equals 0. So as a factor, it would just be an x. Now, when you multiply these, we grouped them together. We took the real part at x minus 2. That's the real part. And we multiplied that together as a quantity, as a pair. So x minus 2 times x minus 2, that's a pair. And when I multiply that pair together, that binomial together, I get x minus 2 squared. I know that if I'm pairing these together, my inner terms are still going to cancel because these are conjugates. So x minus 2 times I and negative I times x minus 2, they cancel. They're going to be conjugates. My last term that I have to multiply is a negative I times a positive I, which makes a negative I squared. I'm going to forget about the x in the front for a little bit here. So now I have x minus 2 squared, which if I FOIL, that's x squared minus 4x plus 4. That minus I squared becomes a plus 1. This all goes together because these two terms up here were from the two quantities I was multiplying together. So I have to simplify that first before I do anything with the x in front. So that expression becomes x squared minus 4x plus 5. That quadratic is how I would end up having the zeros of 2 minus I and 2 plus I. So this quadratic here, oops, came from the zeros, those imaginary zeros. And then all of that is what multiplies with the x, that other 0. So make sure that you're doing everything you can with the imaginary zeros first. Ignore that real 0 in the front until you combine all your parts together. And then if I distribute through, I end up with x cubed minus 4x squared and then plus 5x. Questions? A lot of students had questions on this problem. So we're going to do another one together as well so that you can see a second one. I tried to choose one that was slightly different. Are there questions on number 64? So take your 0, make it a factor, and then do some multiplying. So if we look at the next one, number 65, same directions, except it says find a 4th degree polynomial. So now my power needs to be 4. We have a 2, a 3, and then an I square root of 2. So let's look at these guys. So 2, a 3, and an I square root of 2. Darby, it says 4th degree. We only have 3 here. And what would that be? Yeah. So imaginary zeros occur together in pairs. The reason you have them is because you're taking the square root of a negative number. Anytime you take the square root of any number, you always have a positive and a negative answer. So if you have one imaginary, you have to have its conjugate. Even though it might not be listed, the conjugate is still there. So that would be the little trick to remember. You might only see one, but they always occur together in pairs. Can't have one without the other. And then if we write these as factors, the first one is really x minus 2. And then the second one is x minus 3. Those would be our real zeros. The imaginary zeros would be x minus I root 2 and x plus I root 2. So there's a lot of foiling going on in this problem. Gianna, if we take these pair, the real ones, and FOIL those together, x minus 2 times x minus 3, what do you get when you FOIL them together? Nice. So when you're FOILing, FOIL the real numbers together because they're like terms. Think of them as they're the same type of 0. And then we're going to FOIL the imaginary together as well. I know my middle terms are going to cancel, so I'm going to worry about the first terms and the last terms. So that's an x squared. And then it's I times I makes I squared. The square root of 2 times the square root of 2 just makes 2. So Gianna, if you had x squared minus 2i squared, that really becomes x squared plus 2. And if you think about it, if you tried to solve that factor, x squared plus 2, if you set it equal to 0 and took the square root, I would end up getting I root 2 plus or minus I root 2. So that's how that 0 was created from the x squared plus 2 factor. All right, so we did multiplying here, multiplied the reals, multiplied the imaginaries. Got to do a little bit more multiplying. So Gianna, could you walk us through the multiplying here? And that's your final answer, correct? Yeah. So you're distributing the x squared, and then you're distributing the 2 to all your terms. Combine the quantities together, combine all your like terms, your powers together, and you end up with x to the 4th minus 5x cubed plus 8x squared minus 10x and then plus 12. Any questions? It's a tedious problem. Lots to do in that one. Anyone at home have questions? So the last problem that I had listed on my form, everybody must be okay with finding asymptotes, was number 80, which started chapter 3, and it says to write as a single quantity, which essentially means condense. We want to pull these terms together, condense them. And if you start on the inside and worry about the 1/5 last, it's usually how you work. You start in the inside of the parentheses. Jeremy, what happens with the 3 in front of the first log and the 2 in front of the middle log there? Yeah, so it cubes it or it squares it. So let's change those. I'm going to cheat here and make this a 3 and make that a 2. When you are combining terms with addition and subtraction, you work through a problem from left to right. So if I combine my first pair from left to right, I'm combining 2 at a time. That's really how you add and subtract. You start on the left, just like you read, you work yourself to the right, combining the first pair together. So if I combine them, Jeremy, addition really means, how would I pull them together? If I have 2 logs that are being added, how do we condense? Say it again. Yeah, multiply them. So we would have x plus 1 cubed and x minus 1 squared. And then I still have that minus log 7. I'm ignoring the 1/5 in the front. So combine using multiplication. And now there's a minus sign. I have the log of x plus 1 quantity cubed, x minus 1 quantity squared, and then minus the log of 7. So Jeremy, a subtraction sign, if I'm trying to condense, means divide. So this minus log 7, when we condense them, we will end up having the log of x plus 1 cubed, x minus 1 squared. The 7 goes underneath both of those quantities that are being multiplied together. I don't write the log twice. I don't write log divided by log. The 1 log is sitting out front. Condensing them just means take that 7 and pull it underneath, making it into a fraction. Questions on that? The last thing is still that 1/5. That means my entire expression was being multiplied by the power of the coefficient of 1/5. That coefficient affects everything that's after the log. So all of it is raised to the 1/5 power. Not the log, but whatever's after the log. The log's the function. The part that's being raised to the power would be the exponents, the variables. And then the last step to condense means that that 1/5 needs to be changed as a radical. So it's condensed all the way. My exponent does need to change into radical form. So I have the log, and then we would have the 5th root of whatever's next to the log. And in this case, the x plus 1 cubed, the x minus 1 squared, and then the divided by 7. But take it piece by piece. Don't try and do too much in one step. I know you guys don't like showing a lot of work. It's sometimes with problems like these, they seem like they should be quick and easy, but then you make silly mistakes because you try to do too much in one step. You know what I'm talking about. Questions. So those are the questions that I had on my form. Does anybody at home have other questions that you would like to go over?
Yeah. How do you find the vertical asymptote?
Yeah, let's look, Evan. So if I look at number 70, the vertical asymptote is found when the denominator is equal to 0. So if you take each factor and solve, I would have an asymptote, a vertical asymptote at 2 and a vertical asymptote at 5. So they're found when the denominator is set equal to 0. In 71, this looks like it might be a mistake. 71 doesn't have a vertical asymptote. This might be a Mrs. Kane notation mistake. Oh, there's another answer there. Phew! There's none of these answers. Like, boy, that's not right. Thank you. I didn't see it down there. If I set this equal to 0, and when I solve and take the square root, you get imaginary numbers. Imaginary numbers mean there are no vertical asymptotes. I was worried I made a mistake. So number 71, to find the vertical asymptote, you're still setting x equal to 0, solving for x, but you cannot have an imaginary asymptote. Good question to ask, Evan. Other questions? So before I let you go, I looked at number 81, and just to talk about 82, I'm sorry, not 81. 82 wants you to evaluate that logarithm. And it's the log base A, so you don't know what the base is, but you have 24, and then they give you 2 other logs. They give you a log base A of 2 and a decimal, and then a log base A of 3 and a decimal. To evaluate this, you need to break down 24. So essentially, I need to try and pull this apart and expand it. So 24 can be written as 8 times 3. That makes 24. Well, with properties of logs, if I'm multiplying, I can expand it into addition. So right here, the log base A of 3, I now know that number is 0.6826. If I continue to kind of break this down, what could you do with the 8? How could we write 8? Darby? So we could write it as 4 times 2. How else could you write it, Darby? Yeah, it's 2 cubed. So log base A of 8 is really log base A of 2 cubed, which is actually 3 times the log base A of 2. So here's my log base A of 2. Here's our log base A of 3. So after you expand it, you then plug in the 2 numbers that they give you into that problem. So 83 is similar, but I saw that problem, and I knew when we were going over those were questions that were a little tricky as well. So you have 10 minutes remaining in class. Everybody at home, if you don't have questions, you can feel free to leave and just work on the review. If you want to stay and ask questions, that's fine. Again, tomorrow is the midterm, 15 questions. Please feel free to email me with any questions that you might have as well. Don't hesitate to reach out to me tonight. Have a great day for those of you that are at home. Again, feel free to stay on if you want and ask questions as you're working.
Have a good day.
Thanks, you too.
Bye, Ms. Kane.